Hello students, welcome to this lecture on quantum mechanics. So in this lecture also we will continue our discussion on eigenvalues and eigenfunctions of L square and Lz operator. So before starting this lecture, let me quickly recapitulate what we have done in the last lecture. So what we were doing is that we were finding the eigenvalues of L square operator. So for finding eigenvalues of L square operator, we have first written L square operator in terms of spherical polar coordinates, and this is how this thing looks like. So L square operating on psi is equal to lambda psi. Okay, and we have used the separation of variables. So what we have done, we have separated the solution psi in terms of theta and phi, and because of this the differential equation is also separated in two parts. So one is a phi dependent part only, and one is only theta dependent part. So you can see that this is only your phi dependent part and this is only your theta dependent part. So first of all we have solved this phi dependent part, and we have got the solution of phi, which is equal to e to the power im phi, and the values of m are restricted to 0, plus or minus 1, plus or minus 2, and all these integer values with positive and negative values. Okay, and then we have gone to the theta dependent equation, and here before the theta dependent equation we have used the change of variable. So we have changed the variable from theta to omega, and where the relation was omega is equal to cos theta. Okay, and then we have written the entire differential equation in terms of omega. After that we have assumed a solution of the form p of omega is equal to 1 minus omega square raised to a k of omega. Why I am assuming this form of solution, I have explained it in the last lecture. And the value of a should be always greater than 0. Remember this thing. And so after plugging in this value and choosing 4a square should be always equal to m square, we have came to this equation. Okay, and then we have used this power series method to solve this equation or differential equation, and we have found the eigenvalue of L square operator, which is equal to L into L plus 1, and the value of L basically depends on the value of M. So it is like this. So what we have found, that the value of L square operator when operates on psi is equal to L into L plus 1. Okay, h cut square into psi. Okay, so this is the value, and if L is equal to 0, then the possible value of M is equal to 0. When L is equal to 1, then M will be equal to from minus 1, 0, plus 1. When L is equal to 2, then the possible values of M are minus 2, minus 1, 0, plus 1, and plus 2. Okay, so this is how this values are related. So these are the eigenvalues of L square operator which we have found. Okay, now let me also calculate the eigenvalues of Lz operator, and then we will go to the eigenfunctions. Okay, so we have only calculated up till now the eigenvalues. The portion for eigenfunction is still remaining, and we will do this. So for eigenfunctions, what I have to do is Lz operating on psi will give me some eigenvalue lambda into psi. Okay, I will just since there is a multiplicative factor of IH cross del psi by del phi, I will multiply that with lambda as I have done in this. So Lz operating on psi will be lambda h cross psi. Okay, and we know the expression of Lz, which is equal to minus IH cross, okay, d by d phi equal to lambda h cross psi. Okay, so del psi by del phi is equal to I lambda psi, okay, which implies psi will be having a solution of e to the power minus I lambda phi type. Okay, uh, you can have some normalization constant which I will add later on. Okay, so now e to the power I lambda phi is a kind of solution for this, but you know that the value of phi is limited to 0 to 2 pi. Okay, so after 2 pi it will again repeat the same values, so I can say that e to the power I lambda of phi plus 2 pi equal to e to the power I lambda phi. Okay, so when it is possible, it is only possible when e to the power I lambda 2 pi is equal to 1. Okay, and when this is possible, this is only possible when lambda is equal to either 0, plus or minus 1, plus or minus 2, and all those values. So these are similar to the values of m. So I will call this as m. Okay. So when Lz operates on psi, we'll be having m psi. Okay. Where m is equal to 0, plus or minus 1, plus or minus 2, and all those values. Okay, so these are the eigenvalues of m, of Lz operator, and these values are m. Okay, and you know that we have found here also that the eigenvalues of L square operator are L into L plus 1, and the value of L actually depends on m. Okay, the value of m actually depends on L. Okay, but both of these are interrelated. So how this thing looks like? Okay, so what are the roles of L and m? Okay, so here L is generally the orbital, okay, quantum number, and m is actually the magnetic quantum number. Okay, so this is how this thing looks like. Okay, so this, the figure which you are seeing is for L is equal to 2. So for L is equal to 2, you know that there are 5 possible values of m which are equal to plus or minus 2, plus or minus plus 1, plus 2, plus 1, 0, minus 1, and minus 2. Okay, so you can see that uh, for L is equal to 2, these are the 5 possible orientations. Okay, so you can see that this is the first eigenvalue, which is equal to plus 2 h cross. Okay, and this cone, okay, this cone which you are seeing corresponds to plus 1 h cross. This third thing is equal to 0 h cross. This cone is equal to minus h cross, and this is equal to minus 2 h cross. Okay, so this actually represents what are the total, what are the possible orientations. So you can see that these are the three axes. This is the Lx coordinate, this is the Ly coordinate, and this is the Lz. So these are the three possible or this projections of the angular momentum, and this is how this thing looks like. So this is this Lz uh, axis where this are all the projections of the angular momentum. Okay. Now let me come to the part which we have left, and that is the eigenfunctions of L square operator. Okay, so I will start with this equation which we have derived. Okay. This equation. Okay, so 1 minus omega square, okay, d square k, which is a function of omega, by d omega square minus 2 into 2a plus 1 into omega dk by d omega, okay, plus lambda minus 4a square minus 2a, and let me write that term also, which was equal to 4a square minus m square divided by 1 minus omega square, okay, into k, okay, which is also a function of omega. Here also let me write as a function of omega, and this was all equal to 0. And we have chosen 4a square is equal to m square. Okay, so what will happen? Since 4a square is equal to m square, you can write 2a is equal to plus or minus m. But you know that the value of a should always be greater than 0. Okay, so if a is greater than 0, then 2a is also greater than 0. So 2a should always be positive. But you know that m can have both positive and negative values. So I will always write 2a is equal to mod of m, so that it will always have a positive value. Okay, so this is done. And the other thing is this lambda. So we have now found the value of lambda, which is equal to L into L plus 1. Okay, the eigenvalue of L square operator. So now I have the value of lambda with me, so I will substitute this value, and you can see that there are two terms here, so I can write their mod of m. Here also if you see, then it is generally minus of, okay, 4a square minus plus 2a, so I can write minus of 2a into 2a plus 1, and you know that 2a is equal to mod of m, so I can write this as mod of m plus 1. Okay, so how will this equation look like? This equation will look like this: 1 minus omega square d square k of omega by d omega square, okay, minus 2, and 2a is nothing but mod of m plus 1 into omega into dk of omega by d omega plus lambda is equal to L into L plus 1, and minus, and this term, which is equal to mod of m into mod of m plus 1, and this term, since we have taken 4a square is equal to m square, so this entire term will go to 0, and k of omega equal to 0. Okay, so now this is an important equation, and let me make this in the box. Okay, so now you see this equation, and in this equation, if I take mod m equal to 0, then what will happen? Then this equation will look like this: 1 minus omega square d square k of omega, okay, minus 2 omega d k of omega by d omega plus, and this term will go to 0 since mod m is equal to 0, L into L plus 1 k of omega equal to 0. Okay. Okay. So now you see this equation. Okay. If you remember from your knowledge of special functions, this equation is exactly the same equation which is satisfied by Legendre polynomials. Okay, what is the equation which is satisfied by Legendre polynomials? So if I write the differential equation satisfied by Legendre polynomial, then you must be knowing that it is 1 minus omega square d square p L of omega by d omega square minus 2 omega d into p L of omega by d omega plus L into L plus 1 p L of omega is equal to 0, where PL of omega, okay, is Legendre polynomial, okay, and this PL of omega is written as 1 upon 2 raised to L into L factorial d by d omega raised to L into omega square minus 1 raised to L. Okay, so this is the thing. So you could have easily found the wave functions by matching this two, and you can easily write this. But you know that for our case, the value of m is necessarily not equal to 0. Okay, it can have other values also. So for that case, okay, there is a small modification in Legendre polynomials, and the solution for mod m when it is not equal to 0 is given by associated Legendre polynomial. Okay, so the associated Legendre polynomial is actually written as P L M. Okay, where L and M are basically our L and M values, equal to 1 minus omega square raised to mod of m by 2, okay, d by d omega raised to mod m, okay, and differentiation of PL of omega is actually taken, okay, where PL of omega is nothing but your Legendre polynomial. Okay, okay. So these are the solutions, okay, when the value of m is not equal to 0, okay. So how will this values look like? So if you see the first few values of Legendre polynomials, okay, not associated Legendre polynomials, then for first few values of Legendre polynomials are given as p0 of omega is equal to 1, p1 of omega is equal to omega, p2 of omega is equal to 1 by 2, 3 omega square minus 1, okay, and so on. So corresponding to this you can find the values of this associated Legendre polynomials. So you can find that p for L is equal to 0. You know that the value of m possible is 0, and this will come out to be 1, okay. When p and L is equal to 1, then there are two values. There are actually three values: plus minus 1, 0, and plus 1. But you can see that in this solution, wherever you see m is taken as mod m, okay. So even if I take PL of minus PL, so if I take 1 here and if I take minus 1, it will eventually convert to plus 1, okay. So here P1 minus 1 and P1 plus 1 will eventually have the same value, since in the definition you can see that m is actually mod m, okay. So P1, and for 0, m is equal to 0, it will have cos theta. Now we can say that how this theta came, okay. So remember the definition of omega, omega was equal to cos theta. So I am again converting to my theta variable. So P1 1 is equal to sin theta, okay. Now if I take P2 0, then it will be equal to 1 by 2, 3 cos square, okay, theta minus 1, and P2 1 will be equal to 3 sin theta into cos theta, and P2 2 will be equal to 3 sin square theta, okay. So this is how the values of associated Legendre polynomials are calculated, okay. And now let us see the orthonormality relations for associated Legendre polynomials. So so for omega varying from -1 to +1, okay, d omega PL mod m, and PL prime, okay, of mod m, both are functions of omega, okay. So the value will be equal to 2 upon 2l plus 1, okay, l plus mod of m factorial l minus mod of m factorial, and there will be a Kronecker delta l into l prime. So you can see that when l is not equal to l prime, okay, this entire thing, okay, will go to 0, okay. So you can say that these are orthogonal. Okay. So yeah, this is the main criteria for a varied wave function. Now when L is equal to L prime, okay, 2 upon 2L plus 1 L plus mod of m factorial divided by L minus mod of m factorial, okay. So you can see that right now these are not normalized functions, because you can see that when r is equal to l prime, we should get, for physical relations, we should physical wave function, this value should be equal to 1, and right now this is not equal to 1. So what we have to do, we have to divide this thing with this wave functions, so that this normalization conditions become 1. Okay, so this is a standard practice that we divide this with the solution. So I will write the solutions as, okay, theta L and m, okay, or L comma m is equal to, okay. So what I will do, I will divide this with the PLM, okay, which is the associated Legendre polynomial, so that this becomes a physical solution. So these are the physical solutions. Okay. For physical solutions, the normalization value, the norm should be equal to 1. Okay. So just I have to divide this. Okay. 2l plus 1. Okay. By 2. Okay. And I will write L plus. Okay. I am taking the condition right now where m is greater than or equal to 0. So I can remove this modulus. Okay. L plus m factorial divided by L minus m factorial, okay, raised to 1 by 2, okay, for this entire thing, okay, and PLM cos theta, where PLM cos theta is nothing but the associated Legendre function, and there is a conventional way of writing a phase factor also, which is equal to minus 1 raised to m, okay. And similarly, if m is less than 0, then here you have to write the modulus symbol, okay. So this form will remain the same. You have to just write minus 1 raised to m, okay, theta, and when you are writing m, just replace it with mod m, okay, and which is a function of theta, okay. So this are the solutions, okay, physical solutions of the theta part, okay. So now if you do, okay, orthonormality relations. So it will be now from 0 to pi. Okay, see here we were taking omega, and omega was varying from -1 to 1, but you know that omega is directly related with the value of theta, cos theta. So now I can change the limits of integration from 0 to pi, and it is theta L prime m star into theta lm. Okay, and there was a d omega which is equal to, and where omega was equal to cos theta, so I can write now as sin theta into d theta, and this is equal to L into L prime. Okay, so when L is equal to L prime, I will get this value equal to 1, and when L is not equal to L prime, I will get it equal to 0. So now it is fine. Okay, and now this correspond to a physical solution. So this is the solution of the theta part of the equation. Okay, okay, and you know that we have assumed the wave function psi, which was a function of theta and phi, as capital theta, a function of theta, and capital phi as a function of phi. Okay, so we have already obtained the value of phi, okay, of capital phi, which was equal to e to the power I m phi. Okay, and now we have obtained the value of theta also. So now I can write the total wave function, okay, which is equal to y l m, which is a function of theta and phi both, is equal to -1 raised to m 2l plus 1 by 4 pi, okay, l minus m factorial l plus m factorial, okay, t l m cos theta e to the power I m phi, and here it will be, okay. Basically what will happen that when you will normalize it, you will get a term of under root of 1 by 2 pi also. Uh, so that you have to multiply, okay, and you will get -1 raised to m, okay, the same thing, okay. So this is valid for m greater than 0, and this is valid for y l and minus m, or, okay, you have to just take this complex conjugate, and this will be equal to theta phi, okay, for m when it is less than 0. Okay, so this are basically the solutions, okay, and this ylm theta phi, okay, these solutions, okay, are actually the wave functions, okay, of this L square operator, and these are very famous solutions ylm theta phi, Okay, this are known as spherical harmonics. So spherical harmonics have found a lot and lot of applications in physics. Okay, whenever you are so here we are finding the L square, the eigenfunctions of L square operator, and here spherical harmonics appear. Okay, even if you take multiple expansion in electrostatics, you will get the same thing. Okay, so there are a lot and lot of applications of spherical harmonics in physics, and it is of great relevance. So I just want to show you that how will this wave function look like. So in 3D, okay, so it is actually looking like this. Okay. So this is actually when you plot the spherical harmonic for L is equal to 0. So there is only one possible orientation, that is equal to m equal to 0. Okay. This is actually plotted for L is equal to plus 1. So there are three possible orientations. M is equal to minus 1, then 0, and then plus 1. Okay. Here, since L is equal to plus 1, plus 2, there are five possible orientations. Minus 2, okay, minus 1, 0, plus 1, plus 2. Here, since L is equal to plus 3, then there are 7 possible orientations. Okay, so you know that there are 2L plus 1 possible values. Okay, so since L is equal to 3, so 2L plus 1 values are 7, and here it is corresponding to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Okay, I want to show you that how they look in 3D. Okay, although this image is in 3D, but to have a more visual representation, okay, you can see this. Okay, so you can see this, that how this look like. Okay, so very beautiful simulation. Okay, so this was the thing, and yeah, just one correction here. There will be raised to 1 by 2. Okay, so this is where we will conclude our discussion on angular momentum. Okay, thank you.